The next algebraic structure we are going to talk about is the vector space. Here, we are going to define a new type of operation. It's still a binary operation, but this operation is called an external binary operation. And the difference of this is with ordinary binary operations, on a set A, the function is from the Cartesian product of A by itself to A. Now here, an external binary operation is defined from the Cartesian product of set A with set B to set B. Okay, so we are going to use this to define the scaling operation in a vector space. You see here we have actually two sets, A and B. And so the first operator comes from, the first operand comes from set A, the second operand comes from set B, and the result turns out to be in set B. So this is an external binary operation. Essentially, a vector space is an algebraic structure that involves, first of all, a commutative group with the set V with addition, whose elements are called vectors, hence we name this set V, and also a field whose elements we call scalars. And the vector space satisfies these axioms. Now let's see what these are. With addition, set V constitutes a commutative group, or in other words, an abelian group. So addition is associative, it's commutative. We have the identity vector 0, and all vectors in the vector space or in this group have identity additive inverses. And the next axiom is that this structure is a field F with the operations addition and multiplication is a field. So remember what a field was. Addition is associative, it's also commutative. We have the identity 0. Now this 0 here is a scalar, this 0 is a vector. Do not confuse them, but they are both identities with respect to addition in their respective structures. And all elements in the set F has additive inverses minus C. And multiplication in this field is also associative, obviously, and commutative, since it's a field. And we have the identity, the multiplicative identity of 1. And all elements that are not 0 have multiplicative inverses. And also finally, this product, this multiplication, distributes over addition. And so that's the second axiom. And number 3, this is the external binary operation that we have talked about earlier. This operation scales vectors, and it's an external binary operation such that for all V in set V, first of all, if you scale any vector with 1, the additive identity in field F, you still get the same vector. And for 2 scalars in the field and any vector in the vector space, this holds C1 times C2 times V equals C1 times C2 times V. Now be careful about this. There are 2 types of multiplication here. This multiplication here, C2 times V, is a scaling operation. So it's the external binary operation. Now the result of this is going to be again a vector, and C1 times that is again a scaling operation. But here I have C1 times C2. This is multiplication inside the scalar field. It's not scaling, it's the internal operation of the field, of the scalar field. And what I get from this multiplication is another scalar, and now this multiplication is a scaling operation. So it is sort of an associative property, but the operators at each step are not the same. Be careful about those. And finally, as the last axiom, we have the distribution property. Um, a single scalar distributes over addition of vectors. I should have a subscript 2 here. And also addition of these two scalars distributes over these two scaling operations and then the addition of these vectors. Okay, so this structure defines what we call a vector space. Of course, when we talk about vector spaces, the typical examples we can think of are the higher dimension spaces, like r to the power 2 is the two-dimensional space, and the vectors are coordinates that we provide by giving two numbers, two coordinates, or r to the power 3 is the three-dimensional space. And here, essentially, your vectors are vectors with, let's say, that can be represented by matrices that are m by 1, essentially, or higher dimension vectors like r to the power n. And these are vector spaces over the field of reals. Your scalars come from reals. So when you scale a vector in r to the power n by a real number, what you get is, again, a vector in r to the power n. But this is not the only form of vector spaces. As I said in the beginning, this is an abstraction, and anything that obeys the given axioms, you can define as a vector space and use all the results we have in, let's say, geometry over r to the power 3, for instance. If they can be generalized, you can use them over other vector spaces. For instance, the group of polynomials with real coefficients, if you like, over the field of reals, these are going to be your scalars, constitutes a vector space. Now, earlier we talked about the group of polynomials, but the product operation over there was not scaling. It was the product of two polynomials, like x to the power 5 plus 3x squared plus 2x minus 1. This times x minus 1 is a multiplication in the group of or in the ring of polynomials. However, now I can define scaling like 2 times 3x squared plus 2x minus 1. Now this is a scaling operation. This is my vector and this is my scalar. Okay, I'm treating polynomials as vectors and the real numbers as scalars. And it satisfies, this structure satisfies all the given axioms. Or for instance, the group of functions, the group of continuous functions over the field of reals with the operation of composition or in fact addition also works over the field of reals also constitutes a vector space. Now this vector space is special, especially for communications engineers, because we have direct applications of this in communications. For instance, when we say orthogonal vectors, you would understand this. You have two vectors with a right angle between them, right? This is in two-dimensional space, for instance, or it could also work in three-dimensional space, or you can think this in my new vector space, this one, with the group of continuous functions over the field of reals. Now my scalars are real numbers, but my vectors are continuous functions. For instance, these two functions depicted here also satisfy orthogonality. I'm not going to go into the definition of that, but there are ways to define what is orthogonal, and these two functions satisfy those properties. So we say these are orthogonal functions. And this has direct applications in, for instance, orthogonal frequency division multiplexing, a technology we use in cellular communications. Finally, let me give you a generalization of vector spaces. If the scalar field we use, remember, it's a field of reals or field of scalars, whatever that is. Instead of a field, if you use a ring, so what will be missing is commutativity. You will not have a commutative multiplication of reals. So it will be important in which order you multiply the vector with a scalar. Okay, instead of instead of a field, if you use a ring, what we have is a module instead of a vector space. For instance, in this case, an example could be scalars can come from a matrix ring. Recall that matrix multiplication is not commutative. So your vectors may be, for instance, points in R to the power n, but your scalars, let's say, come from the ring of matrices. In this case, the order in which you multiply or in which you scale your vectors are going to be significant.